The retina contains two types of photoreceptors, rods and cones. Both types have an outer segment composed of membranous discs containing light-sensitive photopigments. Each also has an inner segment that contains the cell nucleus and gives rise to synaptic terminals that contact bipolar and horizontal cells. Phototransduction is the process of a cell absorbing light and creating a response. The response is a change in the amount of transmitter that is being released onto target neurons. The photopigments lie within the disc membranes of the outer segments. In rods, the photopigment is called rhodopsin. The 7 transmembrane domains of the protein portion of the molecule, called opsin, traverse the membrane bilayer. The opsin forms a pocket in which the light-absorbing portion of the photopigment, a molecule called retinal, resides. The photopigments in the rods and the 3 types of cones differ in the protein portion of the molecule, which tunes retinal to absorb specific wavelengths of light. Here, retinal is in a conformation called 11-cis, with cis referring to 2 hydrogen atoms being on the same side of an important double bond. When retinal absorbs a photon of light, a component of this double bond breaks, allowing free rotation about the bond. This change in retinal to an all-trans form triggers a series of alterations in the opsin component of the molecule. The changes in rhodopsin lead to a cascade of events in the cell. The next component in the cascade is a trimeric G protein called transducin, which in its inactive state is bound to GDP. The altered rhodopsin molecule activates transducin, allowing it to exchange its GDP for GTP. The alpha subunit of transducin then activates a phosphodiesterase in the disc membrane. Phosphodiesterase hydrolyzes cyclic GMP, thus lowering the concentration of cyclic GMP throughout the outer segment. As the concentration of cyclic GMP falls, this molecule no longer binds to and holds open ion channels in the surface of the outer segment membrane. Let's compare the action of the ion channels in the light and in the dark. In the dark, the ion channels are open. The influx of the positively charged sodium and calcium ions has a depolarizing effect on the cell. The inward current is opposed by positively charged potassium ions flowing out through potassium channels, a hyperpolarizing influence. The combined result of these ion flows, however, is the depolarization of photoreceptors in the dark. In the dark, the depolarized state of the membrane, which is at approximately -40 millivolts, triggers continual transmitter release from the synaptic terminals of the photoreceptor cells. Absorption of light reduces the concentration of cyclic GMP in the outer segment, leading to the closure of the cyclic GMP-gated channels. As a result, positive charge carried by potassium ions flows out of the cell more rapidly than positive charge carried by sodium and calcium ions flows in. The cell becomes hyperpolarized, that is, more negative, and decreases its release of transmitter. One of the important features of this cascade is that it provides enormous signal amplification. A single light-activated rhodopsin molecule can activate an estimated 800 transducin molecules. Although each transducin activates only one phosphodiesterase molecule, each phosphodiesterase is capable of breaking down as many as 6 cyclic GMP molecules, resulting in the closure of approximately 200 ion channels. This number of channels represents 2% of the number of channels in each rod that are open in the dark, and their closure causes a net change in the membrane potential of about 1 millivolt. Proteins in the photoreceptor limit the duration of this amplifying cascade and restore the various molecules to their inactivated states. Activated rhodopsin is rapidly phosphorylated by rhodopsin kinase, which permits the protein arrestin to bind to rhodopsin. Bound arrestin blocks the ability of activated rhodopsin to activate transducin, thus effectively truncating the phototransduction cascade. By hydrolyzing GTP, activated transducin has a built-in timing mechanism to turn itself off shortly after becoming activated. Without activated transducin, phosphodiesterase also turns off. Finally, through a multi-step pathway, the cell converts rhodopsin back to a form that can absorb light. Also in the dark, the enzyme guanylate cyclase again builds up the levels of cyclic GMP. Cyclic GMP opens the ion channels, allowing an influx of ions and depolarizing the cell.